All right, I am going to talk about, or at least do an example of, finding the potential associated with a single charge. So let's do it with a plus charge of 1 microcoulomb. And let's say we want to find the potential at a distance of 90 centimeters. It could be whatever we want, but I'll go with 90 centimeters. So I'm going to use my equation. V is equal to K times Q divided by R. Now it's a similar equation to the equation for the electric field, but it's different because it's not R squared. It's just R for potential, for the reasons we talked about in a preceding video. All right, so let's do the calculation. We have 9 times 10 to the 9th times 1 times 10 to the minus 6 divided by 0.9 meters, because I've got to convert the 90 centimeters to meters. So I'll rewrite this. 9 times 10 to the 3rd on top. That's the 10 to the 9th times the 10 to the minus 6th, and the 9 times the 1. And on the bottom, I have 9 times 10 to the minus 1st. And the units, again, are going to be volts. So if I do this, the 9's cancel. And I have 10 to the 3rd divided by 10 to the minus 1. I have 10 to the 4th volts, which is 10,000 volts, which sounds kind of scary, considering you get 120 volts out of your wall. So it seems, 10,000 volts, oh my gosh. But it turns out voltage isn't what could potentially kill somebody, it's current. And the amount of current you're going to get from such a small charge is minuscule. So even though the voltage is great, it's not something to be concerned about in this case. All right, so that's an example with just a single positive charge. And I'll follow it through. I'll say, okay, notice that the charge was located, you could say, to the upper right of, the point of interest was to the upper right of the charge. What if the point of interest was located here? Say I'm there, there's my charge, same charge, plus 1 microcoulombs. But let's say I was interested in the potential here, but still 90 centimeters away. I'll mark it with an X. So I should mark that one with an X too. What's the potential going to be at that point? It's going to be the same thing. Potential doesn't have any direction associated with it. It's easier to calculate than the electric field in that regard because it's not up or down. It's just going to be a positive or negative number. And the values that we're finding here are positive because they're associated with a positive charge. Positive charge, if you remember, is kind of like a mountain or a hill or maybe a cone where the positive charge is at the top of the cone and the potential gets closer and closer to ground as you get further away from the charge. Let's see what happens if we put a negative charge here. So let's say if I went negative 1 microcoulomb. Now the equation for potential is actually this, but there is no absolute value sign around the Q here. You need to account for whether the charge is positive or negative. You do for the electric field, but we do that by noting whether a positive charge, what direction it would be pushed. Here, we literally just look at the sign of the charge, whether it's positive or negative. And from that, we deduce what the potential is going to be at some distance away from the charge. So it's going to be equal here to K times minus 1 times 10 to the minus 6 divided by, I'll go with the same, 90 centimeters, 0.9 meters. And K, again, K is 9 times 10 to the 9th. I should have written that in. But I'm going to end up with the same calculation with the exception that it's going to be negative 10,000 volts at that distance away from the negative charge. So if I go 90 centimeters away from this charge here, no matter where I go, 90 centimeters away from it, it's going to be a negative voltage. And it's going to be, of course, along this equipotential circle, just like this one would be here. This one would be here. This one would be 10,000 volts anywhere along that circle. It's not a perfect circle there, but it's going to be 10,000 volts anywhere along that circle. It's going to be negative 10,000 volts anywhere along this circle. And as we get closer and closer to the negative charge, it's going to become a greater and greater negative voltage because this number here will get smaller, meaning the size of this is going to become larger. Same thing over here. As we get closer and closer to the positive charge, this plus 10,000 volts would be a much higher number, closer in. And further out, of course, it would get closer and closer to 0, just as it would over here, too, for the negative charge. All right, so we hopefully are now able to find the potential for positive and negative charges at some arbitrary distance away from the charge. Doesn't matter in what direction the point of interest is relative to the charge, just the distance from the charge to the point of interest. Next, we're going to look at when you have a couple of charges, like a plus and a minus together. What do we do then in terms of finding the potential at some point in space?